Hi, I'm Robert Bolaños. Welcome to Analysis, Design, and Simulation of a Forward Converter. This is going to be part 7, and I'm going to talk about driver circuits. So, in the first, or actually the last video, which was done quite a bit of long ago, I showed a gate transformer drive circuit. Let me see if I can show it. Here is the gate drive. Basically, I'm using a transformer. So let's suppose this is your PWM, and if you have a primary and two secondaries, you can drive the top FET. This is the top FET, and this is the bottom FET, and this would be your primary transformer. And the reason we want to do that is because this node is floating. It's going to be switching back and forth. Basically, when this switch is on, you're going to have 28 volts. Okay. And then when you turn off the switch, we actually have a diode here, and then we're going to have a diode here. So the current is going to try to flow in this direction. So previously this was 28 volts and this is negative. It flips, so then this is going to go negative, and that node is going to be positive. So then this is going to clamp at negative 0.7. So this node basically switches from 28 to negative 0.7. So you're switching, and that is the source, and this is the gate. So when you turn it on, you're going to have 28 volts here, and therefore to turn it on, that means you need at least 10 volts, positive to negative. So that means you're going to have 38 volts here. Okay, and this transformer actually isolates it, keeps it from switching. And actually, there's a little bit of an error here. Should be drawn like this. Like that. Okay, a little bit of an error there. Okay, so this is a gate drive. This is a simple drive, and you can use this if you have a small power supply, not too much power. Okay, now it does have a disadvantage. Let me go back. I mentioned this, that it's good for low power circuits, but you have to be careful that the capacitors will not saturate the inductor. Okay, what does that mean? Okay, so let's look, see what happens. Okay, these are typically going to be electrolytic capacitors. So they're going to be the positive and negative, and positive and negative, positive and negative. They're going to be electrolytics or tantalums. And when the power supply is turned off, let's say you got pulses and then you turn it off, then this is your PWM. It's going to be shorted down to ground. Okay, and if you've been running at 50% duty cycle, and let's say the pulse or the peak, you were driving it with 12 volts, well, 12 volts, 50%, you're going to have an average of 6 volts. So these are charged with 6 volts average. that implies that this is also 6 volts average, 6 volts average. So since you don't have anything, no more pulses, and they're charged, then that charge has to dissipate and it'll flow in this direction. And what does that do? That 6 volts are constantly on the bottom fed, and let me erase this, not make it so much clutter. That means you're going to be applying 6 volts across the VGS of both the top and the bottom. Okay, and that's not a problem, except that if you leave that current on, let's say, typically we've designed it for, let's say, 100 kilohertz. So the duty cycle, or the time period, is going to be 5 microseconds. So we know that the current in the primary is going to go something like this, and then something like that, and so forth. But if the capacitors stay on and discharge very slowly, that means that this 6 volts is going to remain there, and what happens is going to exceed the 5 microvolts, and if they continue, the current will go up and you get a spike, and that's because you're saturating the primary or the core. So you have to be careful with that. So that's the only drawback, that these capacitors, if they discharge, they have to discharge fairly fast, and your circuit may or may not be able to withstand that surge current. So you're going to have surge current. Okay, so that's the gotcha that you have to be careful. Now, if it's a low power, probably won't affect you too much, but if it's a high power, then you may not be able to use this circuit. Okay, so then what circuits can you use? Okay, so a fairly typical circuit that you use is what is referred to as the HiLo driver. Okay, what is a HiLo driver? Okay, so let's take a look at one, and let's cover this too. And I just want to make a statement that for a 2-switch forward, you need a HiLo driver. Okay, why? Okay, so let's go ahead and let's take a look at this one. This one's a HiLo driver. Let me rescale this. Actually, let's see if I can make it a little bit. Okay, so this is a HiLo driver. This is from International Rectifier. It's the IR2110. And if you notice, here is a typical connection. So this is your top driver, and this is your bottom driver. And your primary will be connected like so. Okay, and what's neat about this driver, and let's see if I can explain it. Okay, it's got like a little bootstrap or a charge pump, and the charge pump is this capacitor and diode. Okay, that's very critical. So basically you have that circuit. Okay, but let's take a look at what's inside. Let me see if I have the website. Here is the data sheet. So let's take a look of the inside structure, and basically you have a driver here, and you have for the top, and you have a driver for the bottom. Okay, and you have two inputs. This input is to drive the top, and you have an input at the bottom to drive the bottom, and so forth. So typically these two pins would be tied together. And then they have this gate here. That's a shutdown mode in case you want to shut it down. So that's basically available to you. But what I want to show is that the pins of these drivers are these pins, VCC to common, and then you have this one. Let's call VB to S. So I like to call this the bulk and this the source. Okay, so let's take a look at those two. Okay, so here is the VB, and this is VS. Okay, so what it does when the transistors are turned on, okay, this I said has to be 28 volts, assuming that we're connecting this to 28 volts. So it shorts, you're gonna have 28 volts, and that means, let's say, to turn this on you need 38 volts, or at least 10 volts above. So how do we get this? If we have 28 volts, how do we get 38 volts? Okay, well, this diode, if you look in here, this is your VCC. This powers this, the bottom one, and let's assume, just to make it easy, 10 volts. Okay, so what happens is when you turn it on initially, this will turn on, and if this is 0, let's say it's connected to 0, some of that voltage gets stored in this capacitor. Okay, and when it's turned on, it turns the voltage that is stored in here, and it's routed to the HO, or the high, turns this on. Okay, so remember, this is 28 volts and this is 0 volts. Okay, and then when you turn it off, this is going to fly to 0.7 volts, and then this is going to fly to 28 volts because there's a diode. Remember, there's a diode that goes from here to VCC, and then there's a diode from here to ground that clamps it. So now if you look in here, this is clamped. It's no longer at 28 volts, it's at 0.7. So now it gets to charge that cap during the off time. So remember, this, I'm going to call it V charge capacitor. It gets charged during the off period, where the MOSFETs are off. Okay, so that, and then when you turn on, then this floats up, and that 10 volts is now connected differentially. Basically, so basically now internally you can think of it that this capacitor is connected. Now that it's being charged to 10 volts during the off time, and you want to turn it on, the switches or connects that across the MOSFET and turns it on. Okay, so that's a real nice configuration. You can call it a charge pump or a bootstrap. Okay, so basically that's the way it works. So now, if I want to simulate this, you can do a sub-circuit, and this is the model attempting to simulate this. Okay, so what I did is I put let me see if I can put these together. Okay, so now the MOSFETs I'm simulating them, instead of with MOSFETs, I'm simulating them with switches. Okay, so I have a top switch and a bottom switch, and these are the models that define how these react. So this is the top one. It has an RDS of 6 volts and a resistance, off resistance of 100 meg, and this is the threshold voltage with hysteresis. And then the bottom, same resistance, but it has slightly different threshold voltage and hysteresis. Okay, the reason that I have these here is so they won't cross conduct. Okay, now if you notice, the input is connected to these dependent driver or voltage source. It's a dependent source, and this source is looking at this node. It says V high. So basically it's monitoring that node. Okay, so if this node goes to 10 volts, then it's going to put 10 volts across that, and it's going to turn on the switches. Okay, likewise, the bottom and the top, both are connected to this one, and this one is monitoring this node, VLI. VLI is this node. Okay, and then this is just basically logic gates. Okay, I can put that there, and this is my shutdown. So basically all I have to do is assign some pins. I name them as close as possible. Okay, VB, HiLo, VS, so forth. So now once I have this, it's a hierarchical schematic, then I can go ahead and use it in my top schematic. So here I have the driver. It's the IR2110. So this is the hierarchical driver. Okay, and since it only has a resistance or a turn on resistance 6 ohms, it doesn't have enough current carrying capability. So what I did is I put this little drivers consistent of bipolar transistors to give it enough current capability. So now I'm going to go ahead and test and see how it works. And I'd like to add or talk about these. Right now what I'm doing is I'm running approximately 33 watts, 10 amps, and this should be a 3.3 volt driver or converter, forward converter. Okay, so I'm using the 1N6391. So I'm going to take a look at that just a little bit. Just take a real quick look. Okay, so you can see seems to be working. Now mind you, this is not a closed loop, this is open loop. Okay, but I can take a look at my primary. Okay, this tells me that my primary is working fine, and I can plot voltage from 23 to 1. Let me go ahead and do that. I'm going to plot V from node 23 to 1. That would be the top driver. And I put a comma and 1. Okay. 23 dash to 1. Okay, will it accept that? 23. Expression. Okay, that's not sure why it's doing that. Let's take a look at the bottom one. Okay, so the bottom seems to be working, and it's switching. That looks pretty good. Okay. And let's see, if I type V23 close parenthesis and then V subtraction, let's see, will that work? Expression V23. Interesting. Okay, so it's this node. Should be working. Okay, I'll try it in a little bit. Let's take a look at this. Still running. Okay, so that looks good. And it's approximately 3.3. That looks good. Yeah, 3.3. That looks good. Okay, so let me go ahead and move forward. I want to go ahead and take a look at another part. Okay, because this will set up the next topic, which is how to make the forward converter more efficient. Okay, so let's look at the 1N6391. Okay, and let's see if there's a data sheet that we can look at. And this is actually a huge diode. Okay, so that's a huge diode. That's a let's take a look at this, the spec. Okay, mind you, I'm designing for a 3.3 at 10 amps, so this would probably be a suitable diode. It's a Schottky, first of all, which is fast. And if you take a look here, the voltage or the current rating is, let's see if we can find it. $25 amps. Okay, 25 amps. So you got plenty of margin. Okay. So now let's kind of calculate how much power this would actually consume. Okay. So what we want to do is we want to take a look at this data. Okay. So this is the forward voltage at 25C of 5 amps. Okay. Which is half a volt. And at 50 amps is 0.68. So let's just say, since I'm using 10 amps, let's just bump this to 0.55. Okay. So let's see how much power I would be wasting. Okay. So the power in the diode, and we're going to assume that it's going to be 0.55 volts. Okay. And the current is 10 amps. Okay. So a quick calculation is 5.5 watts of power. Okay. So now the power of the converter, the output, is 3.3 times 10. That's 33 watts. So the efficiency, okay, so let's see what the efficiency is going to be. It's going to be 33 watts divided by 33 watts plus the dissipated watts. Okay, so let's see what that is. So it's 33 divided by 33 plus 5.5 close times 100, 85 watts. Okay, so that's the efficiency. Okay, so we're wasting quite a bit of power. Okay, and I did this so we can go into the next topic, which is, and hopefully I can spell it right, synchronous rectification. Okay, so that will be the next topic. Which is very interesting. Alrighty, so I'm going to go ahead and stop for now, and hope to see you in the next lecture. If you like the video, find it interesting, please subscribe and give me a thumbs up and distribute or share. Thanks.